that's a, quite pleasant, isn't it?
I like that. It's like a coffee shop. Who is that?
This is it's the acoustic channel on Sirius XM. So let's see here, Sam King. Yeah, acoustic guitar instrumental is the name of the channel.
Sam got it all on.
Mm-hmm.
Jordan, hey, no, but. How are you now?
Hi, George. What's going on? Hey, George. Good company here.
You know the last time I talked about friction loss in a hose was? High school.
Been a while, huh?
Double check and make sure this is recording. It is, okay. Good morning, everybody.
Good morning.
Yeah, the song that was on before this was a little bit more peppy than this one.
Yeah, not so funeral music.
It's a little too relaxing. So, okay. First of all, a couple of housekeeping things. I don't have to do a big giant instructor introduction. If I was teaching a bunch of people that didn't know me, I would, but you all know me, so we're not gonna waste any time doing that. I'm just gonna waste some time talking about it, since this has to be 2 hours long. At least, well, this part has to be at least 2 hours long, but, so this is this class is a class I've been wanting to do for a while, but it's also gonna be my Instructor II project. For that reason, you are being recorded. This entire class will be recorded both in here and at the practical skills. So what we're looking at here is we're looking at probably about 2 to 2.5, maybe 3 hours of classroom instruction time, and then hopefully between an hour and a half of hands-on skills time outside this afternoon. We're gonna do the classroom first. We're gonna take a lunch break, might be a 2-hour lunch break, and then we're gonna come back this afternoon and do the skills. So that's gonna tie up kind of your whole day. My apologies, but that's what we're doing. So, so there's that. I want to make sure everybody's got everything they need in front of you. You should have a student manual. It says student manual on it, and you'll notice as you look through that is an interactive student manual. So there's fill in the blanks and places for you take notes and things like that, to kind of keep you engaged. I think this topic is pretty exciting, but I'm kind of a nerd. So I understand it's not quite as exciting as some people. But hopefully we can get some interaction and discussion and talk about some things that you're gonna learn some things. Some of you have been doing this for a long time. This is gonna be, most of this is probably gonna be pretty basic to you. You're gonna know it. I would ask you, if that's the case, to use your experience in discussion in the class to help educate some of those who don't have as much experience. We'll talk about kind of the details of what this class is after we go through what you're supposed to have here. You should have a class evaluation that looks like that. So that's your evaluation of the class. You'll turn that into me at the end. Notice you don't have to put your name on that. So when you do write dirty and mean things about how terrible the class was, I won't even know who it was that wrote it. So there's that. And then you'll have 2 skill sheets. Those are front and back. One is pumping from a static source and one is pumping from a pressurized source. You'll have those. And then you should also have 2 different laminated tools. One of them is this half sheet laminated smooth bore discharge data. This is basically just a printout, kind of a pocket guide that you can keep that tells you different sizes of smooth bore nozzles and what their flow would be at a given PSI. So we're going to get into, in this class, we're going to get into a little bit, not super deep, but we're going to get into a little bit of GPM versus PSI and what we're looking for at the nozzle. Because ultimately that's what we're trying to achieve from the pump panel is optimum nozzle operations, right? So, and we'll talk about that more in a little bit. You'll also have this laminated sheet, which has 2 different documents inside of it. The first one is a pressure loss calculator. Something you need to know about pressure loss, and we'll get into more, is it's all theoretical. Okay, so we're going to talk about all these numbers and how this is and this isn't. Just remember, it's all theoretical. So it can vary, but these are, this is a lot of math that's been done over a lot of years, and a lot of scientific studies that have come up with these numbers. This chart's really helpful because you can just look at it and you don't have to do the FLQC squared. But it's just something you'll get into when you get into the state driver operator class, if you should happen to take that, or if you have taken it. On the other side is a pump discharge pressure guide that I made for our specific nozzles. Again, these are estimates. These are estimates. This is what, if I were running the pump on our truck with these nozzles, this is what I would set the pump at initially for those individual type nozzles and hose pressures. So what at some point maybe we can hang one of these inside the driver compartment, and it's just there, and you kind of have a quick reference guide to go, okay, I'm throwing my 1 3/4 pre-connect and it's a solid bore. I can set my pump at 150 and know that that's the pressure that I'm trying to pump at to start with. So does everybody have all of that stuff? Yes, okay. If you don't, let me know. If something happens to one of those throughout the course, let me know and I'll get you another one. But I just want to make sure everybody had that before we go. This is an adult class. If you need to get up and go take a phone call, if you need to get up and go pee, if you need to get up and stretch your back, if you need to get up and walk around the classroom, that's perfectly fine. I'm not, we're not in elementary school, so I don't expect you to sit at your desk quietly. In fact, I kind of expect you to speak up and have a lot of conversation in this class. Otherwise, it might be kind of boring if we don't have some discussion. But yeah, I intend to stop every 50 minutes and have a 10-minute break. So we started at about 10 after 9, so right at about 10 o'clock we're going to stop and we're going to take a 10-minute break. During those breaks, I would ask that you keep them to 10 minutes, and I don't have to go rustle people up to get them back in here so we can keep the day going. We do have Chief Coulter and I have a lunch appointment today, so with our medical director, so I'd like to get out of here in time to go have that lunch, and then we'll come back for the afternoon. All that being said, if it comes to be lunchtime and we don't have the classroom portion done, no big deal. We'll come back and we'll finish it, and then we'll go out and do the practicals. We got all day. So there's that. As you know, there's bathrooms right there. There's bathrooms in the back. You know where they're at. If you need anything that I can provide you that you don't know how to get yourself in this station that you work at, just let me know, and I'll help facilitate that. So the class title that I came up with is "Bring Me Water." The funny thing about this, it's kind of a what do you call it? It's kind of a sarcastic title, or an oxymoron, because that's kind of an insult in the fire service. When somebody says "bring me water," it's like, we're going to get there first, and you're going to bring me water. But I kind of think of it as what pops into my mind when I think about this is the old Budweiser commercials that would talk about some dude that does something in the background that is actually really. You guys remember those? Here's to you, Mr. Yeah. Here's to you, Mr. Whatever. So I always thought there should be some firefighter related ones, like, here's to you, Mr. Hydrant Man, while all the other people are at the house getting their gear on and getting ready to fight fire, you're making sure that they have water so they don't die. Nobody wants to be the hydrant guy, right? You want to be in the fire. Nobody wants to be the pumper that's bringing the pumper that's fighting the fire water. But the truth of the matter is that that's really, really important. It's really, really important to be the guy that's giving the people water that are going in, because if not, they will die, or they might die, or things are not going to go well. So this is a really important, I would argue, one of the most important jobs in the fire service is running the pump of a fire truck. A lot of times we tend to focus on driving the fire truck because there's so many safety issues, and that's what you're doing more often than not if you're driving. But if you're driving a fire truck and you're not an efficient pump operator, then you need to get better, because that's one of the most important tasks on the fire ground. Nothing else on the fire ground can happen safely without that. The fire can't get put out without that, and people get hurt when pump operators don't know what they're doing. I've seen countless times on both career fires and volunteer fires where the pump operator struggled to get water for various different reasons, and usually it's because they don't really understand the scientific process behind what's going on in the pump, and something happens that's outside of the context that they were taught. Pull this lever, push this button, do this thing, and that's how you get a pump to work. And that's all they ever know is pull this lever, push this button, do this thing. Well, then if something happens between pulling this lever and pushing this button that didn't happen when somebody told them to pull this lever, push this button, and do this thing, they lock up and they don't know. So that's what we're going to hopefully address in this class, is in between pulling the lever, pushing the button, and doing the thing, all of the things that are happening inside the pump, and all the ways that you can deal with issues that might rise up when in between those things. So, and why you're doing those things, because that's one of the things I think we don't take the time to teach people is, why are you pulling the lever and pushing the button and doing the thing? What are you causing to happen other than, well, you're getting water to come out the end of the hose? Well, yeah, I know that, but like, what's that mean? There's a lot of different ways water can come out the end of the hose. There's effective ways and non-effective ways, and water coming out the end of a hose does not mean an effective fire extinguisher. So, bring me water is, when I was a driver in my career, I took that as a compliment, not as an insult, because by God, I am going to bring you water, and it's going to be the most efficient pump operation you've ever seen. And that's the way I prided myself in being able to operate the pump the best that it could be. So that's what I want all of you to do as well. So that's why it's called Bring Me Water. This is a basic fire pump operation class, and I did not set up my little clicker, so let me see if I can set that up real quick. Basic fire pump operation class. Again, I do encourage discussion. Course goals. We want to give pump operators a better understanding of the science, the terminology, and the mechanical processes involved with producing effective fire streams. Now that's a lot of words, right? So I basically want you guys to have a basic understanding of what is happening at the chemical, the molecular level in water that causes it to do the things that we want it to do to put the fire out. I want you to understand all the terminology that we use, PSI, GPM, and flow, and all that stuff, so that when we're using those terms on the fire ground, nobody's confused. I want you to understand the mechanical processes. In other words, now that I understand what the water's doing and what all that stuff is called, what do I do to make all those things happen? That's the mechanical process involved with producing effective fire streams. Is there a difference between an effective fire stream and a non-effective fire stream? Yes? No? I mean, I could kind of get technical on this and say no, because if it's not an effective fire stream, is it really a fire stream, or is it just water coming out the end of the hose? But I would say that I'm going to go out on a limb here, and I'm going to say most of the time we are not producing an optimal fire stream when we're pumping for various different reasons, and we'll get into some of them here. But I'd say most of the time, not just we, but the fire service in general, is failing at producing effective fire streams. Just like in EMS, just like all of the studies with CPR and some of the team CPR that we're doing now compared to what we were doing 3 or 4 years ago, you see, now you know what effective CPR is compared to just CPR. So we're going to learn what an effective fire stream is versus just a fire stream. I want you to gain some level of comfort and confidence with the mechanical processes in a low stress environment. So I don't want you to have to learn this when you're under pressure. I want you to learn it in a low stress environment so that when we do have pressure, you can do it without getting worried or without messing up. And I've said this before, you guys have heard me, I use the term broadband or broadband width. Your brain only has so much broadband width or bandwidth. And every little thing that you have to think about on the fire ground takes up bandwidth. And so what we try to do with basics is we try to get these to be muscle memory, or we try to get you comfortable enough with them that you don't have to use a lot of bandwidth to perform these functions, these basic functions. That way, when things get more complicated, you have bandwidth left to use to solve problems. Because that's what we do for a living, is solve problems, right? And it shouldn't be any different we know we solve other people's problems for a living, but it shouldn't be any different when we're solving our own problems. Because problems come up when we're doing fire service. When we're pumping a truck, problems come up. And we should be able to have bandwidth to solve those because we know what we're doing with the mechanical process. So those are kind of the main course goals, and those are the two foundational reasons why I wanted to write this class. Confidence and comfort. All right, so your learning objectives, we're going to have two different kinds of learning objectives. We're going to have course objectives and lesson objectives. You'll also see, in your lesson plan and your student manual, I use the terms classroom objectives and practical objectives. I just think that those terms are more easy for us to understand what we're trying to achieve. These are the terms the state wants me to use, so there you go. Course objectives and lesson objectives. Course objectives are going to be taught in the classroom and measured by written evaluation, or what we call a test, but we're not supposed to call it that. I guess that's scary for people these days. And then a lesson objective, they'll be taught in the classroom here, and then they'll be reinforced with hands-on training. So by the book, those are practical objectives. They'll be measured with a skills assessment. So this is no different than anything else any other class you've done that's like a certification class in the fire service. Same thing. You're going to have lesson objectives that are going to be taught and measured by a written test, you're gonna have, course objectives, and you're gonna have lesson objectives. They're gonna be taught, practiced, and then displayed by a skills test with a checkoff sheet, and that's how you're gonna pass the class. Instead of using the terms pass and fail, we'll use the terms succeeded or needs more work. You know, because there's never going to be a time when you know everything about all this. I don't know everything about all this, and you're always going to be learning. And everybody's going to be at a different level because of experience or because of their skill level or whatever. So, all right. So your course objectives or your classroom objectives are going to be identify and list the working parts of a pump panel. The pump panel that we will be using for this particular class just so happens to be Pumper 71's pump panel. So this is kind of a twofold purpose for us. I want you guys to get used to that new pump panel that you're not used to. So we'll be both in class and in skills, we'll be using that pump panel, and that'll be building those muscle memories in your brain so you're not taking up broadband width. Number 2 is you're going to distinguish the differences associated with pumping from the booster tank, an external static water source, and an external pressurized water source. And again, remember, we're going to talk about the terminology of what all that means. So by the end of this class, you'll know where stuff is on a pump panel, how it works, and how to pump from the tank and from various different external sources. Your lesson objectives or your practical skills objectives, given a scenario, I'm going to want you to establish an effective fire stream from a pressurized water source. I'm going to want you to establish an effective fire stream from a static water source. And I'm going to want you to predict pump behavior, capability, and functionality based on the needs of a given fire service, or a given fire scene. So, in other words, when you're pumping, as you add more lines, or as you, let's say, transition from the booster tank to the fire hydrant, things are going to change, right? The things that your pump is doing is going to change. Nozzle pressures are going to change. Those are the things that I need you to predict behavior-wise. I need you to know what the pump's going to do when you pull the lever, push the button, and do the thing. Or pull the other lever, and push the other button, and do the other thing. I need you to know what the pump's capable of, because as fire scenes grow, you're gonna find that your capabilities are limited by not just by the pump, but by your water sources, by your manpower, by your time, by various different things. You're going to be limited. Your capability is going to be limited. You need to know what your limitations are and what your capabilities are based on those limitations out the gate. And you need to be able to roll with the punches too, because we might be calling mutual aid. They might get here and they might not. We might be tagging a plug, and it might work or it might not. You know, there's always stuff that can happen. And then functionality is just, that means I want you to know what the pump is going to do when you do the thing. Okay? If I pull this lever, what happens? If I push this red button, what happens? You should know everything on your pump panel. You should know what it does and how it affects other things. All right. Things don't always go as expected, so this is just a fun little video, and this worked 2 days ago. Didn't really want to work very well yesterday, so it just kind of plays into the fact that things don't always go as expected, but hopefully it works. It's about 6 minutes long. Just enjoy. Oh, there may be some language in this video, so my apologies. But be prepared for that. There is some language in the video that's not necessarily appropriate for young viewers.
Oh!
What the fuck?
I've seen this in Kansas City more times than I want to say.
Look how little it is.
It's like a golf cart bumper. Whoops.
Crazy directions.
Knowing your capabilities. You know, some chief probably told him to do that.
He's keeping that river wet.
Should we use real costs?
There's a fire suppression system under there that will try to help put that out. It tried to help, but that fire is what was left of the flat tire on the right front brake road. These brake roads are ridiculous new. And what happens is,
I remember when that happened.
remove the ultimate.
You're fucked now.
some of that is firefighters doing what firefighters do. But in almost all of those instances, there was some sort of unexpected, unfortunate event that could have been prevented by either effective training, practice, or just general preparation. Okay? So that was kind of the point of the video. I was trying to find a video that was geared more driving, and there was a lot of driving stuff in there, but you get the point. Like, there's always something happening on a fire scene. Every fire scene ever. Something's going to happen that you didn't expect. And so we have to be prepared for things to happen that we don't expect. And if the only thing we've ever done as far as pump operations is learn to pull the thing, push the thing, and do the thing, then we're not prepared for unexpected events. So that's what we're trying to accomplish with this class. All right, so some discussion. You'll notice in your student manuals, I think we're going to start kind of getting to the point where you can fill in some blanks there. Those student manuals are for you. I'm not looking at them. I don't care if you write in them or don't. It's up to you. We're all adults here. But so what is a fire apparatus for? Can somebody tell me what is a fire apparatus for?
Transporting personnel and suppression items to the scene.
Okay, so I would agree, except by definition, that's just an apparatus. That could be any type of apparatus could transport people and equipment, right? You're not wrong, but by definition, fire truck does do that. But to be called a fire apparatus, what does it have to accomplish?
Be able to fight fire.
Okay, in what way?
Have a pump water.
Okay, we're getting there. It's got to have a pump. What's the pump got to do?
You got to put out enough water.
It's got to put out enough water to do what?
Create an effective fire stream.
Thank you. That's exactly the definition. I knew we'd get there. The main purpose of a fire apparatus, in order for it to be considered a fire apparatus, is that it has to provide adequate pressure for effective fire streams. Okay? Now, I don't like this definition. This is definition by the IFSTA manual, the driver operator IFSTA manual. I don't like this definition, and I'll tell you why. Because effective fire streams, pressure only has a little bit to do with making an effective fire stream. But, so it's kind of misleading, but essentially what the pump does is it pressurizes the water, and then we use that pressure in order to convert it to an effective fire stream. And that's what we're going to talk about today, is how do I make that pressure become effective? Because, what is water under pressure? It's just water under pressure, right? But just because I put water under pressure, does that make it an effective fire stream? No. It has to move the right direction. It has to get to the right place, right? So, but that is, by definition, the main purpose of a fire apparatus is to provide adequate pressure for effective fire streams. So I kind of set you up there, Lance. Sorry.
Okay.
But what makes a fire stream effective?
Ability to put out fire.
Yes, by definition. So what exactly? But what are some specific example? Okay. So what is a BTU?
British thermal unit.
And what does that mean?
Heat.
Okay. So a BTU is a measurement of the amount of heat, right? So you're right. A British thermal unit is a specific amount of heat. It's a measurement of heat. So what are we trying to do to the BTUs? We're trying to reduce the number of BTUs, right? So in order to do that, we have to have an effective fire stream. How do we reduce the BTUs?
Take out the fire triangle.
Okay, putting enough GPM, but why?
Can overcome the BTUs to cool it.
To cool it, thank you. So, or I like to use the term to convert it. Because what we're doing, the way that we cool this, and this is right out of the Firefighter Essentials Manual. What we're doing to cool the fire, or to reduce the amount of BTUs, is we're using water to convert those BTUs, or that heat energy, to steam. Okay? When water converts to steam, it dissipates energy because it expands by 1,700 times. on the molecular level, okay? So a molecule of water, or whatever, say we got 10 molecules of water, we convert that to steam, and now we have 17,000 molecules, okay? So we know if you cool hot water, it makes a bunch of steam. And like you imagine, I'm trying to imagine when you boil water and you with the lid and you take the lid off, how much steam comes off of that pan. And it takes a long time to boil all of that water, right? If you took a pan of water and you wanted to boil it until it was gone, you could. How long would it take? Depends on the amount of water, right? But how much steam would that produce? And it would make everything in the kitchen wet, right? So you're taking that water that was in a centralized location, and by converting it to steam, you're spreading it out, you're covering more area, and you're making it last longer. Does that make sense? That's what we're doing with water. That's what causes fires to go out. And producing an effective fire stream means that I want to maximize my water's potential to convert heat energy to steam. That's my way of explaining it. That's what we're doing. So I think it's important to know the what behind the why, or the why behind the what. So that's what we're trying to do. So that's what makes an effective fire stream. And before we move on, Brian is exactly right. When it comes down to the rubber meeting the road, what produces an effective fire stream is gallons per minute. That's the way that we measure the amount of water that we're putting on a fire. That's what produces an effective fire stream, is gallons per minute, or GPM. The more GPM we can get, the quicker the fire goes out. But is GPM limited? Absolutely. Because if I've got 1,000 GPM, but it's only coming out of the end of the hose 4 feet, what good is that doing me? It's got to get to where I need to get it. So it's got to be harnessed in a way that it can get to the seat of the fire effectively without putting us in too much danger, and in a way that we can handle it and all these other things. So we know that different sizes of hose, different types of nozzles are all different ways to get the most GPM that we possibly can to a given fire, given a certain situation. But there's a reason why we have so many different nozzles and so many different fire sizes. All right. How do we produce an effective fire stream with a fire apparatus? And by the way, these are just discussion questions. So, but how do we use a fire apparatus then, knowing what an effective fire stream is? How do we use a fire apparatus to make that?
GPM.
But how do we make GPM from a fire apparatus?
RPMs.
Okay, that's a good answer. RPMs equals GPMs to a degree, right? What does RPMs cause inside the pump? Pressure. Okay, so now we're getting back to this. RPMs equals pressure, essentially, in a fire pump, and pressure equals GPM, sort of, in a roundabout way. Because if I take a bowl of water, let's just say I got a bowl of water this big, and I just put water in it, and I set it on a table right here, what is that water going to do?
Sit there.
It's just going to sit there, right? It's not going to move. It over time it'll evaporate because of just atmospheric pressure and differences in humidity and things like that. But for the most part, it's just going to sit there. If I had, let's say I've got a 2-gallon bowl of water sitting on a table here, how long do you think it would take for that bowl to be empty if I just set it on the table right there and walked away? Months, maybe more. I mean, I don't know, because it all depends on the humidity in the room and things like that. But it's going to sit there for a really long time. It's going to grow stuff in it and all that stuff too, because it's just sitting there. Water is a very passive molecule. It just wants to be left alone. That's the way I like to explain it. So on the molecular level, it's a hydrogen atom and 2 oxygen. There's a 2 hydrogen along. A hydrogen and 2 oxygens, and it's just sitting there. And as long as you just leave it alone, it's just gonna sit there. It does nothing. It just sits there. Now, if I've got this bowl of water here, I should have got a bowl of water. If I was a good teacher, I would have. But if this bowl of water is sitting here and I take my fist and I go bam to the bottom of the bowl, what happens?
Water comes out.
Water splashes everywhere, right? Why?
Can't
Well,
be
because water molecules want to be left alone. And this is an oversimplification, okay? We're getting a little bit out of, I'm using science to be allegorical, okay? But if I take my fist and I slam it into that water, I've upset those water molecules because they just wanted to be left alone. And when water molecules get messed with, they move. That's what they do. What we're trying to get the fire pump to do is move water. So we have to upset those water molecules. There's two ways to really upset water molecules. One is heat. The other one is pressure. Our pump actually produces both. In fact, pressure produces heat. And if we produce too much pressure inside the pump, it'll produce enough heat that then water will start turning into steam inside the pump, and that's what causes pump cavitation, essentially. So, does that all make sense? Water wants to be left alone. If we disturb water, it will move. So what are we trying to do? We're trying to disturb water. And we're trying to use the most effective way that we know how to make water move as quick as it'll possibly move, and that's by introducing pressure to it. You introduce pressure to water, and it's like, I'm getting the heck out of here. And it's going to find a way out, no matter what. And that's how the fire pump works. We figured out a way, not we, but somebody along the line figured out a way to take water that's just sitting there and add pressure to it, and then when it's under pressure, direct it to go a certain direction, because it's going to go somewhere, and that's how we have a fire stream. Pretty cool, I think. I told you I was a nerd, but that's the kind of stuff that like gets me to thinking, okay, now I know what I'm trying to do with this water, you know, and I'm trying to get the water, so I'm trying to get the mad water out the end of the hose, so when it encounters heat, it's already under pressure. When it encounters heat, then it's going to be really mad, and it's going to be so mad it's going to metamorphosize into steam, and then the steam's going to put the fire out. We're going to keep going. When you guys get back, we'll be where we're at.
1300 Broadway Street in Pleasant Hill.
So then what is GPM? Gallons per minute, all right? So that is the way that we count how much water is, the camera's on, yes. So if you don't want to be on camera, don't.
I just want to make sure I didn't.
So if GPM is the way that we measure how much water is coming out the end of our fire hose. That's what we want to know. That's ultimately what we want to know, is how much water is coming out the end of my fire hose. And I will tell you, back in the day, in the 80s, even, and maybe even in the early 90s, the fire service still largely thought that pressure is what put water out. I mean, what put fire out. So like, we were building all these nozzles that would generate a ton of pressure, but not much GPM. Because we thought that we essentially thought that pressure is what put the water out, or the fire out. But science and studies have shown us that that's not what puts the fire out. We do need enough pressure to get the water to the fire, but what we really need is just lots and lots of water. So what's PSI then? Pounds per square inch. And so that's what we measure the pressure by. Because we need pressure to move water, we need to know how much pressure we need to move water. Does that make sense? All right. So then that all boils down to what pressure should I pump at? And Josh and Jake are the only two students in here that have ever pumped a fire pump. So what pressure do I pump at? Depends on just that? I mean, no, it depends on a lot of things, right? You're right. Size of hose, size of the fire, how far how many hoses I have, what nozzle I'm using, who's on the end of the line, how many people are on the end of the line. What, back in the day, we used to just say, run the pressure up till their feet come off the ground and then back it off a little bit, And that's how much pressure that's how we knew how much pressure to pump at. You know, that's great unless you can't see them because they're inside the house. And really that's more of a joke than anything, but I'm telling you, back in the 90s in the volunteer fire service, there were people that lived by that. Like they didn't know anything about the numbers behind the pressure. They would run it up until their firefighters got on the radio or waved their arms or something and said, "That's enough, Billy Bob, turn it down." You know, and then you got your firefighters at the end of the hose that last like 3 minutes because they're fighting the pressure of the hose, and they wonder why they can't get the fire put out. And we're going defensive, and then everybody just sits around on a 2.5 inch curled up in a circle, spraying water at the fire while the newspaper shows up and all their families and friends, and with 15 teeth between all of them, and just I'm thinking specifically of a town in southern Missouri in the Ozarks, or something like that. But nothing around here would be like that. But anyway, it's important to know the numbers. It's my whole point. There's a reason why we have numbers of PSI. In America, we use PSI. I think in other countries they use KPA. That's the metric version of pressure measurement. And I just want to say, I don't know why we don't just go ahead and go to the metric system. It would be easier. I support it every inch of the way. I don't know why other people don't. So, all right, what's the difference between pumping a solid bore and a fog nozzle?
One produces a fog stream and one's a solid bore. One produces.
Well, that's the difference between the pattern, but what's the difference between pumping them?
They're different pressures.
Okay.
GPMs.
Different pressures, different GPMs, right? So the first thing we need to know is that there is a difference between pumping a solid bore and a fog nozzle. If I put a solid bore nozzle and a fog nozzle on the end of the same exact hose line at the same exact fire, I'm going to need to pump different pressures to achieve my optimum GPM. And that's what we're trying to achieve, is optimum GPM, right? How much GPM can I get out of this nozzle on this hose line and have my firefighters still be able to effectively fight fire? So I'll tell you this, with a solid bore nozzle, you can essentially, the more pressure you put to it, the more GPM you're going to get. And it is limited eventually, but like the solid bore nozzles we use, we're not going to pump to their limitations GPM wise. What's going to limit us is the nozzle reaction. As you saw on the video, with the one guy standing there and he's spraying water, and then all of a sudden he falls over backwards, that's because the pump operator increased the pressure all of a sudden. What probably happened is he hooked up to a hydrant. He was pumping from booster tank, he hooked up to a hydrant, and he didn't mind his discharge pressures as he opened the intake valve. We'll talk about that as we move along, but that's the difference between a solid bore and a fog nozzle. We're trying to achieve different GPM, and there's different ways to do it. And we'll get into how we know. How do we know what pressures that we're trying to produce out of a fog nozzle or a solid bore nozzle? What about master streams? What do we pump master streams at? What are master streams? You hear the term, what's it mean? Anybody? By definition, a master stream is a fire stream that produces 350 gallons per minute or more. Okay? So, a master stream, to think of it practically, is a hose or a system that can be used that's not a hand line. All right, so you can use 2.5 inch hose can be a hand line or a master stream. So when you curl it around in a circle and you sit on top of it, it's a master stream. When you two go inside with it and you're fighting fire, you're getting to the seat of the fire, you're moving with it, it's a hand line. Could I be pumping 350 GPM out of a hand line? Yes. By definition, it's a master stream, but that doesn't necessarily make it a master stream functionally. Does that make sense? So we have a new master stream device that's going on the new truck. It's the Mercury master stream nozzle. It'll go on a 2.5 inch line. It's capable of producing anywhere from 250 GPM all the way up to 750 GPM, supposedly, out of a 2.5 inch line, and it's an adjustable nozzle, but the way that you're gonna, but it's a portable monitor. Essentially, you can set it up on the ground and use it as a master stream, or you can use it as a hand line, the same nozzle. So that's but that's your difference between your master stream and so on. So 350 GPM, I must have been clicking the button. 350 GPM is what is considered a master stream. How does drafting work? It's 10 o'clock, let's take a 10-minute break. And when we come back, maybe some of those guys will be back and we can answer the question of how does drafting work.
So on the pump master stream, how do I pump it? What would be the answer? I know what it is, you said 10 gallons per minute or more is a master stream, but what does that mean?
Well, the question, the answer to the question is, it's complicated.
Okay,
And that was the point of the discussion,
okay,
was to show that there is no one answer to any of these questions.
okay,
So,
there we go.
but that's a good question. Thanks for asking.
I didn't know if you know, I didn't know if you were missing a person, so I'd come listen. And I have pumped a truck. I mean, not very long and not very well,
Did you know
and I had somebody helping me.
Did you know what you were doing, or were you just pulling the thing?
I was just, yeah, here you go. I was being told what to do.
Yeah.
so it's not fancy, but it is extremely thought out. Everything flows.
I was looking at like how it's like right in here, it's like your house
Yeah.
is.
Yeah, if she had the budget to do what she wanted, the house would look different every couple of years. And we don't, and I'm thankful because I hate that stuff.
So,
Yeah, but we have an apartment in the basement. That's where my daughter's living right now. And we're good. And, well, we gave all the living room furniture from that apartment to our son when he established himself in an apartment down south. Well, now Elizabeth's back from being out back east for the summer, so we had to get that set up. So we ended up buying a absolutely ugly and atrocious little sectional thing that Rhonda and Elizabeth love, and they just think it looks amazing. And it's very well decorated in there. It's just not my style at all. It just looks horrible.
All right,
I
let's,
mean, it's not basic, so everybody else loves it. And I'm just like, no.
let's go ahead and carry on. Those guys will be back in just a few minutes. So, the question we left with was, how does drafting work? Anybody care to? Not exactly.
Pull water from there, put it in there, pressurize it, put it out there.
You don't pull it though.
I'm sorry, you're right, because it's all gotta be pushed.
So how does it work? And this is a, I don't expect you guys to necessarily know the answer that I'm looking for. I'm sure you guys know how to do it.
creates a vacuum.
It doesn't create a vacuum. What it does is it creates a void, and then atmospheric pressure pushes the water into the pump. Okay? Then it uses the siphon effect to keep water in the pump, right? So that's how it works. A lot of people want to use the term suck or whatever. We even call it hard suction hose, but it's not actually sucking. It's not actually vacuum. It's just using atmospheric pressure to push water into the void. And that's how it works. But operationally, at draft, everything going out of the pump works exactly the same way as it does if we're pumping from any other source. Whether we're pumping from a booster tank or a pressurized source, drafting, it's no different. Once we've established draft, which there's a process there and we'll talk about it, but once we've established draft, it's all the same. Putting water out of the pump. We still need to know what pressures we need to achieve optimum GPM out of a given hose, a given nozzle, or a given device, right? And so that's important to know as a pump operator. You should know every device that you could potentially flow water through on your truck, and you should know what the optimum GPM is and how to achieve the optimum GPM out of every single device that you could possibly flow water out of your truck. And I would argue that in the fire service in general, there is a severe shortcoming in people who operate pumps knowing all of that stuff. But that's what makes an effective fire stream, is knowing what pressure to pump to achieve optimum GPM, why and how. All right, so here's the next discussion question, and we've probably already answered this question, but why do the answers to all these questions matter? If I can just be taught to turn the pump on and pull this thing and push this thing and do this thing and it makes an effective fire stream, then why should I care about all this other stuff and all these numbers and all this mumbo jumbo?
Things happen.
Because things happen. And if you don't know why the truck is doing what it's doing, or how the truck is doing what it's doing, when something happens, you don't know what to do. It's no different than being a paramedic or an EMT. We learn, to go to paramedic school, it takes, 14 months to 2 years on average, and we learn a lot of stuff in paramedic school that we really don't ever functionally use necessarily in the scene. I mean, or on a scene. Do I need to know the physiological process of Graves' disease to know how to do an IV or to give somebody fluid, like the way that I would treat Graves' disease? I mean, whatever their symptoms are, I'd probably give them an IV, maybe give them some fluid, take their vital signs, and get them to the hospital, right? Why do I need to know how Graves' disease works? Well, because if there's a complication in my treatment or my treatment plan, then I need to have a secondary plan in order to treat that patient, right? I need to know that that disease process can cause other disease processes and can trigger other pathology, medically speaking. So, same thing with a pump. I need to know more about the pump than I functionally need on a scene in most cases, because if I'm flowing an 1 3/4 line on a solid bore nozzle and I got one attack team in the fire and everything's going hunky-dory, but then my hydrant goes down, do things substantially change at that moment? I've got people inside. So I need to know what my next step is and how to deal with that. Or I've got a crew inside and another crew shows up and I need to put a second crew inside. Or the fire grows and I need to increase my hose size from an 1 3/4 to a 2.5, and I've got a limited amount of water because my source is limited. It's either, bad hydrant, or I don't have, or I'm drafting and I only have the porta tank full and that's it. I need to know my capabilities. I need to know my pump's capabilities. I need to know how fast that water is going to run out. And the only way I can know that is by math, by numbers. It's a 2,000 gallon tank. I'm pumping a 2.5 inch line at 250 GPM. How long is it going to take me to go through that tank of water? It's simple math, right? 2,000 gallons, 250 gallons per minute. So it means every 4 minutes I'm pumping 1,000 gallons, right? So I got 8 minutes. As long as if the nozzle's open at the most. And those are all theoretical calculations, so I would give myself a little bit of wiggle room. So that's why it all matters. And here's some of the reasons that I think it matters, and I just found some of these quotes. A good firefighter knows how, an educated firefighter knows why. So I may know how to get water to come out of the pump, but to know why the water is doing what it's doing is a whole different story. And that's what differentiates a good pump operator from a pump operator. If they can't say it and they can't show it, they don't know it. So if you can't tell me why the pump's doing what it's doing, then you don't know how. You don't know what you're doing. You're just a monkey, essentially. You've been taught to pull the lever, push the button, and do the thing. And as long as you can pull the lever, push the button, and do the thing, everything's okay. But the minute something introduces itself from the outside that causes you to have to variate from that, you don't know it. You got to be able to say it, and you got to be able to show it. And that's why we have a written test and a practical skills assessment sheet. A written test is you saying that you know the information. Practical skills is you showing that you know the information. Nothing will work unless you do. So this goes a little bit deeper than just the work on the pump panel. It takes work to know this information. It takes effort to be good at this job. And if we I wish more people were in here because I really wanted to lecture on this. If we're spending all of our time sitting around waiting for the call, then nothing's going to work the way we expect it to, because we're not working the way we should be. And that's the bottom line. That's the truth of the matter, is the more you work to know this information and to be good at it, the better it's going to work when you're on a scene. The less broadband you're going to use, or the less bandwidth you're going to use, and the less complications you're going to have. Period. I can almost always watch any video that I watch or any fire scene that I see where there's complications. You can almost always trace it back to a lack of training, which could be an administrative issue, but more often than not, it's just an issue of people not wanting to get off their butts and train. So that's enough, I'll move on. Before you can think outside the box, you have to know what's in the box. Learn the basics. I thought that was really, really neat because I harp on that all the time. Basics, basics, basics. Until you're good at the basics, it doesn't do any good to try to think outside the box because you don't even know what tools you have to use to think outside the box. Is that all? I guess that's all. All right, we'll move on to the working parts of a fire pump. So, if we look at this truck here, with the body pulled off, this is your engine, your truck, the motor that powers the truck. This is your fire pump. You can see you have a transmission right here. That transmission takes the power from the engine to these back axles through a drive shaft. It makes the axles spin, uses U-joints, transfers power to the wheels, so on and so forth. The truck goes. There's a power takeoff in here that takes power from that drive shaft. It essentially turns the drive shaft off and turns the pump on. Does the same thing. Takes the power from the engine and powers the pump. The pump, to make pressure, has to spin. Just like the drive shaft has to spin to make pressure, or to make work happen at the wheels. Pump has to spin to make pressure. And that's essentially the way a fire pump works. Everything that you're seeing right here is the pump housing. There's other parts here, little parts, but you could call essentially, well, really the pump housing is technically right here in the middle, but I guess I'd call this the pump body. I also have a picture over here of the various parts of the inside of the pump of a single stage fire pump, which we use a single stage fire pump. Nobody, unless you're industrial, you're not going to see a two-stage fire pump anymore in municipal fire departments. But I actually had this before I had this, but we can go over here and we can see the by number. We can see the impeller shaft assembly, which is this shaft right here is the impeller shaft. This is the impeller. Right here, this big golden disc. That's where the magic happens. That's what makes pressure. The second thing we have is the intake valve, which in this one is right here, but we know our intake valve, it's an Akron Revolution intake valve. That's where the water comes into the pump body. This one has an air primer. Ours also has an air primer. It's not a Venturi, it's a Trident, but it's the same thing. It takes, there's another motor down here that's a primer motor that's activated by air, and what that does is that under pressurizes the pump body so that atmospheric pressure can push water into the pump body. So just sitting there, because it's not a vacuum system, just sitting there inside the pump body, if atmospheric pressure is 14.7 psi at sea level, what do you think the atmospheric pressure is inside the pump? It's 14.7 psi at sea level. So I have to do something to change the atmospheric pressure inside the pump so that the atmospheric pressure outside the pump can push water into the pump. That's what a primer does. Does that make sense? Your discharge valve, there's various discharge, there's a bunch of different discharge valves, but this one here is a discharge valve. You have your intake relief valve, which keeps too much pressure from coming into your pump body. So if you have a really strong hydrant, or if you're pumping on a relay or something and they're sending you a ton of pressure, that could damage the pump body. It could damage the internal parts of the pump. So we have an intake relief valve that takes some of that pressure and relieves it so that it doesn't get into the pump. You'll see that, and the way that you'll see that happening is you'll see a bunch of water squirting out on the ground underneath your pump at your just inside of your intake. That's the pressure relief valve doing its job. Discharge relief valve, same thing. Discharge relief valve, it protects the firefighters. Most of them nowadays are built in to a certain pressure. Back in the day, you had to set your discharge pressure relief every time you pumped the truck, even on an engine, the one we just got rid of. had a manual relief pressure valve, right? So you had to turn your pump on, crank the wheel till the light came on, and then back it off a little bit. And that was the relief valve. And then the screens would get plugged up every now and then, and it would get stuck on. You gotta take it apart and clean it. They're much simpler these days. Your tank to pump valve is right here. For some reason, people have a hard time understanding what the tank to pump valve is. So I'll spend just a little bit of time explaining what the tank to pump is. Because people just call it the tank to pump. They don't ever call it the tank to pump valve. So first thing, it is a valve, just like any other valve. It might be a ball valve, it might be a butterfly valve. There's various different setups of types of valves it can be, but it is a valve. So it opens and closes to let water through, or to keep water from coming through, right? Just like any other valve. What it does, if you think about what it's called, is it takes water from the tank and puts it into the pump, okay? So when you have that valve open, your 1,000 gallons of water on our truck has a 3-inch line that runs from the tank to the pump. When you open that, you're getting a 3-inch line wide open. It's gravity fed. So, you know, you got 1,000 gallons of water in a square tank. The less the water is, the slower it moves. But, you know, water's standing water has 0.434 pounds per square inch. So the higher it is, the harder it pushes. That's the other thing about water, is it sits still as long as it's in a closed container, but if you let it out of the container, it wants to get flat. It wants to run off.
That's 3 inches pretty standard across most engines, pumpers.
From what I've seen, yeah. Anything bigger than that, it's really easy to cavitate your pump with your tank to pump valve open, because you can actually, a lot of times you can feed back through these. Sometimes, especially on older engines, this valve, it's just one valve for tank fill and tank to pump. Back in the day, that's what a lot of trucks were that way, is a two-way valve. So you open it to get water from your tank, you also use it to put water back into your tank. Nowadays, most of them aren't like that. Your tank fill valve is a whole different valve, but it's just kind of important to know. When I open the tank to pump valve, what am I doing? I'm taking water out of my tank and putting it into my pump, all right? Pneumatic shift is number 8. That's what shifts the pump into pump gear. Your shift interlock is basically keeps the pump in gear, and then your transmission is what powers the pump, what takes the power from the engine and makes the pump go. So those are kind of your working parts of the pump. We're getting on the edge of probably knowing more than you need to know to pump, but that kind of stuff helps me to understand the process of what's going on. Like, what is a pump actually doing? How does it work? So that kind of answers that question. And with that being said, this is about an 8-minute video on basic pump theory. Enjoy.
Hi, my name is Jay Rott, Senior Service and Training Specialist for the Waterous Company. Today we're going to talk about basic pump theory of a centrifugal pump. We're going to start with the CM pump and CS pump, midship style. We're going to talk about bringing the water in from the intake side of the pump through the impeller out to the discharge. Right? Basic components. The bronze impeller, that's standard in the fire service. Resistance to heat, resistance to corrosion. The basic parts of this impeller. Very center is the bore. It's pressed onto the impeller shaft. There's a keyway cut into it, so it's keyed on. We're going to trap the impeller shaft in the impeller axially. So we use a C-ring or a retaining ring on the back side of the impeller, a lock ring or a nut or a snap ring on the front side, depending on the design. Now, whenever the impeller shaft rotates, the impeller is going to rotate with it. Right? Around the bore is the eye. So where the water comes to from the outside source comes in the intake side of the pump into the eye of the impeller. Inside the eye are the 5 blade-like things in there. Those are the veins of the impeller. So it's actually going to create the centrifugal force to move the water out of the impeller. Around the eye is the hub of the impeller. That is the main point of wear inside the pump. When you rebuild a pump, this is typically what you're going into rebuild, is this area right here. Around the hub of the impeller is the front shroud. Okay? On the back of the impeller is the back shroud. And then we have the exit way of the impeller, where the water comes out. It comes into the eye, comes out of the exit way, whenever the impeller is turning and rotating. All right? Now we cut away the back side of this impeller so you can see how the impeller actually functions. So the veins of the impeller start off in the eye of the impeller. And centrifugal actually means that the force starts in the middle, makes its way towards the exit way. Okay? And what an impeller actually does is adds velocity to the water, speeds it up, makes it move faster. As this impeller rotates, this side of the vein will hurl the water out of the impeller and send it out towards the exit way of the impeller and out into the pump body, to the discharge side of the pump. Again, what an impeller is doing is adding velocity, speeding the water up. As the water is sped up, it's going to be thrown out into the exit way of the pump and then out towards your discharge. Right now, the outside of the exit way of the impeller, it's a sealed vessel. The water can't go anywhere until you open up a discharge valve, open up the nozzle on the end of the hand line. When that's all closed, it's a sealed vessel. That water is being thrown into the discharge side of the pump, will now create pressure. Okay? When you open up a discharge valve, open up the nozzle into the hand line, you now are going to open up that pressure inside the pump to atmospheric pressure. Water is going to seek that lower pressure outside the pump. So the impeller has to rotate in that direction. Okay? Again, adding velocity. Now, as far as the impellers, before we ship them out or before we can put them into a pump, they have to be balanced. So we set the impeller on the machine. It's got graduation marks around the pedestal on the side of the impeller. That's going to spin, and then the machine will come up and tell us at that graduation point, point 230, that so many ounces over. Okay, so they'll take the impeller off of the pedestal, grind it at a certain spot, put it back on the machine, spin it again until it comes up and says it's a true part. Okay. Now, let's go inside the pump. So now we're going to go over and look at the S100 in the centrifugal impeller inside the pump body. Okay. Bronze impeller, just like we talked about before. We're now going to direct the water from the intake side of the pump to the discharge. So if you notice, the impeller doesn't set in the middle of the body. It's pulled over to one side. It's closer on this side than it is over on the other side of the impeller. This area we're creating is called the volute of the pump. It's a pathway for the water to follow. Okay, so the water is going to move in that direction. The impeller is going to rotate, adding velocity to the water, spinning like that. So this particular pump, the S100, has 2 volutes. There's a top volute and a bottom volute. So this volute here, and then the bottom volute of the pump. The water always seeks the path of least resistance, or a high pressure will seek a low pressure. So when we tuck the impeller over tight to the side of the pump body, we're creating an area of high pressure. As it comes around going out to the end of the volute, it's lower pressure, so it's a pathway for that water to follow. Okay? The other thing we're creating at the end of that volute is called the stripping edge. It's a knife-like edge which cuts the water off of the impeller as that impeller rotates. So we have a high pressure on this side coming around, getting cut off on this stripping edge. We have another volute that starts here that comes around and it gets cut off on this stripping edge. Comes off on this side of the pump. The 2 discharges do come together at the end of the discharge flange here. Centrifugal pumps are not 100% efficient. Some of the water you put in is not going to come out. It's going to stay inside the pump body. It's going to circulate inside the volute area. Okay? The main point of the inefficiency inside a centrifugal pump is actually the water coming off the discharge side of the pump back into the intake. Okay? We can't seal it off completely. We have to do something to restrict the flow of water from the discharge side back into the intake of the pump. What we use is called a wear ring, okay? Or a clearance ring, some people call it. But it's a piece of bronze, the same basic material as your impeller. Okay? And as this is put inside the pump body, the wear ring is trapped in the body. So on an end suction pump like that, that's the wear ring here. It's been cut away on this section so you can see the outside of the impeller. But this is trapped in the intake adapter. Inside of a midship style pump, we have actually two halves of the pump. We have a bottom half and a top half, the body portion, and we machine a bore inside the pump for the wear rings to set. The bore that's machined into the pump body is actually smaller than the OD of the wear ring. When we put the two halves together, that seizes the wear ring in place. It can't turn. It's pressed into place. And when the impeller shaft assembly is put together, the hub of the impeller fits inside the wear ring. So now the water, when it wants to circulate back into the eye, has to come out the exit way of the impeller, down the front shroud, and then it has to go through the clearance back into the eye of the impeller. Okay, increasing the efficiency of the pump, keeping the pressure on the discharge side. The clearance between the hub of the impeller and the wear ring is about 3 to 7 thousandths of an inch diametrically around the hub of the impeller. That keeps the pressure on the discharge side of the pump. We have 3 different types of wear rings that we use. A conventional cut, which would be like this. So going on to a standard impeller hub. So it fits over the hub of the impeller. So the water comes down out the exit way, down the front shroud, through the clearance, back into the eye of the impeller. Okay, that's the conventional cut. We also have a wraparound, which is the water comes out of the exit way of the impeller, down the front shroud, and around the hub of the impeller back into the eye of the impeller. What we've been using since the 70s is called the Labyrinth Reverse Flow Wear Ring. The wear ring actually has a stub that sticks out of it. Okay, so it sticks out on one side. The impeller has a recess cast into the front shroud that when assembled, the stub that sticks out fits back inside the recess. Okay. Now when the water wants to circulate, get back into the eye of the impeller, it has to come down the front shroud, on the outside of the recess, on the outside of the wear ring, back towards the impeller, down, then through the clearance back into the eye. Reducing the flow by making the water move and break as it comes back into the eye of the impeller, making the impeller more efficient.
Isn't that interesting? I think it's interesting.
I can only imagine how fast that thing has to spin in there.
Yeah, it spins pretty fast, but, you know, I mean, think about it though. You talk about, we use centrifugal fire pumps, and if you ever take the state driver operator class, they'll get into history of pumps and where we came from, positive displacement pumps and all that other stuff. But in the fire service today, by and large, we use centrifugal pumps. The way centrifugal pump works, as he says, it takes, it puts pressure from the middle to the outside. So if I took a towel and I dipped the end of it into a bucket of water, and then I just hold it up like this, what's the water gonna do? It's gonna slowly drip back off the bucket. But if I take the towel and I do this, where's the water gonna go? It's gonna go on all the walls in this room, because that's centrifugal pressure. I take force from the inside, push it out. It pushes it off the end of the towel, and it slings it under pressure until it either gravity brings it to the ground or it hits a stopping point. He said something I should have said earlier, is that when I said water is lazy and it wants to be left alone, it's always seeking the lowest pressure it can possibly find. So as it's sitting in a container, and I said when some of you guys are out of the room, water, sitting still water has a pressure of 0.434 pounds per square inch. So it's always under a little bit of pressure. As it's sitting in a container, it's putting pressure against the walls of the container. If I remove the walls of the container, what does the water do? It flattens out, right? It seeks the lowest pressure it can find, and it goes as far as it can go until gravity or another object stops it. And so the way that the fire pump works is, and you saw like the reason that the pump is offset in the volume is because that gives the water a gradual decrease in pressure, and it's always going to seek less pressure, so it knows where to go. If that were all the same size, it would just kind of spin around in the pump, and some of it might happen to go through the discharge just because of it has nowhere else to go, but it wouldn't seek the discharge. But because of the way the pump's built, it goes high pressure to low pressure to low pressure to low pressure. It seeks the discharge, because it just follows the path of low pressure. And it tries to get out, you know, when you open up the nozzle, it's going from whatever the PSI you have it at, 100 PSI to 14.7 PSI is the atmospheric pressure. So that's why it shoots out of there so fast. It's like, oh, you know, oh God, there's a lot of low pressure out here, you know, like, get me out of here. And so it goes out, and then little does it know, it's gonna go through the fire and turn to steam and you know, get dissipated back in the atmosphere and start its process all over. But such is the story of being water. Some of it might even get broken down into individual atoms, and it has to go be some other thing altogether. Anyway, whatever. I can really get into that nerd stuff, but I always like the chemistry a little bit. All right, so the pump panel. This is our pump panel off of our new truck that we will be using for the class. Bear in mind, every pump panel looks a little bit different, but they all have the same stuff on them. What's on the pump panel is actually set forth by NFPA. Now, I didn't put any NFPA numbers in this class. This is a basic pump operations class, and I think it's kind of silly that we have to memorize all these NFPA numbers, so you don't have to worry about that. But just know that NFPA has a standard that says everything that's supposed to go on a pump panel, okay? So they all have the same stuff. Some will have more bells and whistles than others, but our pump panel, we'll start with the pump controller, this right here. This is the brains of the pump, okay? Back in the day, this would have been a twisty valve that had a throttle cable that ran back to the motor that would increase the throttle, thus spinning the pump faster, thus increasing the pressure. It still has a spinny thing, but newsflash, just so you know, there's nothing connected to that spinny thing. It's just a computer. When you spin it, it sends a signal to the computer that says they want more pressure. The computer tells the thing to give you more pressure. Tells the engine to bump up the throttle and all that. We call that the throttle valve. It's not truly a throttle valve. It's just a computer control, is all it is. Really nice if it's working right. And it's really nice to be able to set a pump in PSI mode and then know that whatever pressure I've got it set at, it's going to keep that pressure regardless of outside influences. So like if I'm pumping from the booster tank and I've got it throttled up to achieve my pressure, when I open a hydrant and that water comes in, it's going to drop the throttle, it's going to drop the RPMs on its own to achieve that pressure. And it's just reading a number. It's reading a pressure gauge that says they want this much pressure going out of the pump no matter what, and it takes that into account and then it reads that. Now, we haven't gotten to the point where it's closing its own valves, but I wouldn't be surprised if by the time some of us retire that you just key in a pressure on any given valve and it just does it all. It opens its own valves and everything. I would hate that. I already don't like this because I was brought up where I ran everything. But it is really nice when it works well. So that's your pump controller. So on your pump controller, before we move on, just so you know kind of what's all there, on our pump controller, it has 4 buttons. This button, it puts it in PSI mode. This button puts it in RPM mode. That's real simple. It says pressure and RPM on it. What's that mean? In pressure mode, the controller works off of a discharge pressure that you set, and it tries to keep the master discharge pressure at that pressure at all times. Now, if I have my master discharge set at 135 and I've got 3 lines going off at various different pressures, all the pump controller knows is that I want my master discharge pressure to be 135. It doesn't help it, I can set this line at 110 and this line at 120. It doesn't know that those lines are set at 110 and 120. So it can potentially mess with those pressures at the end of the line. So you do still have to man the pump. RPM mode says it says you want a certain RPM, and what it's using is it's using engine RPMs I don't know what the conversion is to pump RPMs versus engine RPMs, but, so, you know, I set my engine at 1,000 RPMs or whatever, and that's, so it knows, I want the engine to be at 1,000 RPM, and it's gonna stay. So it's more like old school pump operation where you had the throttle control, and you know, it's just stays constant unless you change it. Then you can change your pressures by gating down valves and stuff like that. But if you open up a pressurized water source and let it into your pump, it's gonna bump the pressures up substantially on your discharges if you don't lower the RPMs, right? So just functionally, that's how it works. Those are what those two buttons do. One of these is a menu button that goes through different readings on this readout, which tells you your oil pressure, your oil temperature, your water, the engine functions to make sure that your fire engine is in good health. You can check all that stuff. I think there might be a fuel gauge on there. I have to look at it again, but I mean, there's quite a few things that you can cycle through to check, you know, oil pressure, water temperature, things like that of your engine. And then the other button, I think, is a diagnostic button. We'll have to see when we get out there. I don't remember right offhand. I can't see it on this diagram. But what you're going to use 99% of the time is that throttle valve right there. In the middle of that throttle valve is a button that says idle. And no matter what setting your pump is in, and no matter what pressure you're pumping or what RPM you're pumping, if you push that red button, it drops the pump back down to idle. It drops the engine down to idle, which drops the pump down to idle, no matter what. It's kind of nice for when you're shutting down, or when something goes wrong and you need to reassess. But you can also turn the valve or turn the controller the opposite direction. I think left is up and right is, I don't have to get out there.
Counter's down, yeah. Left
Yeah.
is down.
Yeah, okay, so left is down, right is up. All right, so yeah, because on the old valves, it was righty-tighty,
Yeah.
lefty-loosey.
Left higher,
Yeah.
right lower.
Yeah, so anyway, you can do it manually, but just so you know. Generally speaking, we might get into this later too, generally speaking, when you're shutting down, we don't really get much into shutting down in this class. But when you're shutting down, it's always better to idle down first and then close valves. Just like when you're opening valves, it's always better to open valves before you throttle up, because it's easier on the valves. There's less pressure against the valves that way, and it's just easier. It's easier for you, and it's easier on the valves. It's easier on the people on the end of the line. Anytime you can, now there's times when you're adding lines or whatever, you're gonna have to do it under throttle, but generally speaking, if you can open your valves and then throttle up, do it. And when you're shutting down, if you can throttle down and then close your valves, that's much better on everything, on the water system, on everything. It reduces water turn. For some reason, we don't have any new pump operator, well, George, but for some reason, new pump operators struggle with that concept. But like, they just want to slam the valve shut, and they're like, "Can you get this valve shut?" Yeah, because your pump's at 7,000 RPM. All that pressure is against the valve, so just remember that. Your pressure gauges. This pump does not have any GPM gauges. They are all pressure gauges. Okay. It does. No, I don't think it has any flow meters at all on it. So all of your gauges are pressure gauges. These are all individual pressure gauges for each individual discharge valve. These are all discharge valves. So when you pull this, it opens the valve. When you close it, it closes the valve. If you take these valves, you pull it out and you turn it half a turn, it locks the valve. Just so you know. So like if you're operating on a fire scene and you don't want your valve to get bumped closed or something, it's a good idea to turn it, that half turn, it locks the valve, it won't push in or out that way. A lot of pump operators, you'll see, they turn them straight up and down even when they're not pumping. I don't particularly prefer that, but you know, that's fine, as long as you know that that's the way to lock them. Let's see here, this right here is your tank volume gauge, so that tells you how much water you have in your tank. It's just a LED light that goes down as the volume. It's not 100% accurate, it's just an estimation, so just so you know. This is all your scene lights and your air horn right here. So you have an air horn at the pump panel in case we need to do an evacuation signal. And your scene lights. This is a discharge. There's only one discharge. Obviously, we have 3 pre-connected lines. Actually, I have 4 pre-connected lines on that truck. We have 2 discharges on the captain's side and 1 discharge on the driver's side of the pump. And I think we might have 3 discharges on the captain's side. But that's your, let's see, pre-connect, 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 deck gun. That's a discharge on the captain's side. So we, no, that's on the back. These 3 are on the captain. So you got 3 on the captain's side, 1 on the back. You got a deck gun. You got this one, and then you got all your front bumpers down here.
Yeah.
That's your front bumper. So those are your discharges. This is a 2.5 inch discharge, and this right here is this is for this is for your front bumper.
You've got this listed on here in our little workbook, dischargers. There's a types, and it's the link next to it, so.
Oh, yeah, okay, so types of discharges are, where did I put my lesson plan? So I can tell you the right answer. Hold on. In some of those cases, I just put stuff to keep you engaged, but I did put a specific type in my lesson plan here, so. Pre-connected, gated, and open are the types I put, but you could probably think of more types too. But like I said, pre-connected, gated, we actually don't have any gated discharges on this truck. Or is the one on the back gated? It's not, is it?
The intake.
The intake, but not the discharge, okay. But you do, like some trucks do have gated discharges on them where there's an external gate that you control. And then I would call this an open discharge. Good question, thank you. Your cooler valves are over here. On this truck, you have a pump cooler and a heat exchanger cooler, which is essentially your engine cooler. So a lot of people ask, when would I open those? I would say crack them open anytime you're pumping, unless if you're like using every single bit of water you can possibly use and every single PSI is necessary, and you have to close those to get that 5 PSI back, then fine, but otherwise, just open them. Because the truck's sitting still, especially in the summertime, the truck's sitting still, it's running at a high RPM, there's no air moving through the radiator, so what this does is it takes water from the pump, and it moves it through the heater core, which cools the engine temperature down.
If it's below freezing, I typically don't open them.
Yeah.
Because in my head, I heat the water
Yeah.
up a little bit and
Yeah.
then sit it down the hose.
That's good thinking. That's good thinking. And like, just know what they do and know why they're there. And different pump operators are gonna have different ideas. Your pump cooler keeps the pump itself cool. As long as you're flowing water out of the pump, out of the hose, you would really never need to open that because you're always getting fresh water inside the pump. But it's for situations where you're not really moving water through the pump and it's just sitting there. What that does is it takes water out of the booster tank just a little bit and just constantly introduces it into the pump to cool the pump down. Like I said earlier, as that pump's spinning and creating pressure, it creates heat, and we don't want the heat to get too hot. It can cause, not only can it cause pump cavitation, but it can also cause excessive wear on the pump and things like that. Master intake valve, right here. This is a secondary intake. Some people call this the steamer valve. Generally speaking, on any pump panel, your intakes are going to be lower than your discharges. So if this had 4 discharges on it, they would all be above the intakes. Your drain valves are what's going to drain a particular line between the outlet and the pump. So any water that's left inside of the pathway from the pump to the discharge end, it drains that. So every discharge on the truck has to be plumbed from like these pre-connected discharges, they have to be plumbed from the outside of the pump up to here. So that pathway will hold water unless you drain it. Does that make sense? In the wintertime, it's really important to keep things drained because they will freeze up and then you won't have water when you need it. Another thing that's not on this list is this right here, is your tank to pump valve that we talked about earlier. This right here is your primer. Did I miss anything?
Tank fill research.
Oh, thank you, yes, your tank fill is right here, tank volume gauge, so, yeah, and Lance called it a tank fill and recirc. That's because a lot of people, or a lot of trucks now have it on the valve. It's just, the way that you can recirculate water if you're not pushing it out of the pump anywhere, is you can open that tank fill valve, it'll send water from the pump back into the tank, and then as long as you have your tank to pump open, you'll be taking fresh water in from the tank to the pump. A lot of older trucks, as I said earlier, when some of you were still in here, that was the same valve. Your tank fill and your tank fill and your tank to pump were essentially the same valve, and water could just freely move back and forth. It's two different valves, and it's good that it's two different valves. But just remember, your tank, if you open your tank fill and you're pumping only off your booster tank, you don't have an external water source, you're not really recirculating water unless your tank to pump's open. Well, in fact, you'll just cavitate your pump.
You have to have tank pump on to pump water.
Yeah, but when you first turn your pump on, it's gonna have water in it unless you drained it. I've seen people do this, that's what I'm talking about.
Very little, yeah.
It'll have water in it, and if you don't turn your tank to pump on and you open this tank fill because you wanna recirc water,
I see what
you're gonna empty the pump and you're gonna cavitate it. I just did a state evaluation a couple of weeks ago for driver operator class, and almost every single person, the first thing they did was open the tank fill valve. Somebody told them that they needed to recirculate water, and that was the first thing and the most important thing that they needed to do. And I understand probably why they told them that, but it's important to understand what you're doing. If you don't have the tank to pump valve open, you're just emptying your pump, and then we got problems. Anyway, probably stuck on that longer than I needed to. Yeah.
One of the things that it's not on there physically anymore is we used to have the relief pressure valves we
Yeah.
could set. It's now in the control panel, but it's only in the pressure mode, because if you go to RPM, you override it. So it only works.
Yeah, we talked about that a little bit before you got here. Another thing is that this intake also has an external pressure relief valve. So you have a pressure relief valve on the intake, and you also have a built-in pressure relief valve inside the pump that's controlled by the computer, and Brian's right, it only works if it's in PSI mode. If it's in RPM mode, it doesn't, but this one still does, because it's just a mechanical.
Because we used to be able to set it ourselves, and now they preset it.
Mhm.
Whatever you tell them.
Yeah. And this one is adjustable. I think it's set at like, I'd have to look at it, I don't know. Okay, time for a break anyway. That's the way it goes. We try to teach a class, they're gonna run out of calls.
You can respond to the area 58, 57 in Pleasant Hill for an NBA. I think 1-800 at the time, Pleasant Hill, trying to get more information.
PD got, you see what?
Right where they're doing road work.
PD, got toned on like 5 minutes ago.
Did you hear where the other info was?
Copy of all, if you just.
No, I didn't.
She'll be back soon.
I don't know.
I copy it, and if you just.
They just cleared or if they're cleared or everything.
Where'd they go?
Copy it.
Lee Summit?
Went to Lee Summit Medical?
St. Luke's East.
That's gonna be east.
Yeah, it must go to east.
I was gonna say, if they're at 470 and 50, sir. I have my glasses in case I need to see something.
I'm gonna go ahead and pause this video and we'll just pick up after lunch.
Kellenberger called off.
Oh, he did? Well, that makes lunch work.